Associate Professor in Production Engineering Department of National Institute of Technology, Tiruchirappalli, Tamil Nadu. He completed his PhD from PhD College of Technology, Coimbatore. He completed his master's degree in production engineering from PhD College of Technology, Coimbatore, and a bachelor's degree in from Government College of Technology, Coimbatore. He was a gold medalist in his undergraduate and postgraduate studies. He has been awarded National Doctoral Fellowship for pursuing research by AICT New Delhi. He has been awarded Highly Commended Paper Award and Outstanding Paper Award by Emerald Publishers UK for the year 2009 and 2011. He is a recipient of Institute of Engineers Young Engineer Award for the year 2013-14. He has published over 100 papers in international journals. He is on the editorial review board of various international journals in the specializations of manufacturing and industrial engineering. His research interests include the production and sustainable manufacturing, agile manufacturing, rapid manufacturing, product development, and Industry 4.0. So I welcome you, sir.
Okay, thank you, Dr. Manikandan, for the introduction. Okay, so let us proceed with the session. Let me share my content. Is my content shared visible?
Yes, sir. Yes, sir.
Dr. Manikandan, is my content shared visible?
Yes, sir. Yes, sir. Visible, sir. Visible.
Okay, so if there is any interruption in the content display or in my voice, kindly inform me. Okay.
Okay, definitely, sir. Definitely, sir.
I ensure my network is appropriate, but still, if there are any interruptions, you bring to my notice. Okay.
Oh, sir. Definitely, sir. Definitely, sir.
Is my voice clear? Okay.
Yes, sir. Clear, sir. Clear, sir.
Okay. Good morning, all faculty participants and scholar participants for this short-term training program. So in this session, I'll be discussing on the concepts of 3D printing and Industry 4.0. So I planned my session in two modules. The first module is on 3D printing and the second is about Industry 4.0. So let this session be interactive. So any questions you may kindly post in the chat box. Okay, interimly, let me take up the queries for discussion. And at the end, we shall have certain discussion. And as faculty members, you all know the objective of any short-term training program, the discussion will aim at starting from certain fundamentals and moving ahead with the further developments and to see about some research aspects. Ultimately, connecting academia and industry in such a way, I plan my session. So let me begin with the discussion on 3D printing. So in this first module, I plan my session in such a way we'll discuss on rapid prototyping, tooling, and further about manufacturing, and the about 3D printing and the popular process concerned with 3D printing, and to go ahead with certain case studies of 3D printing. Okay. So first, let us see how this 3D printing technology has emerged. So when we look about the historical perspective of this layered manufacturing, as we all know, this 3D printing and other technologies, they belong to layered manufacturing technologies. And of course, other experts might have spent some time on discussion over these topics. I would like to make my discussion unique in the sense, let us quickly discuss about the historical perspectives relevant to the discussion which I planned, then to go ahead further with the advancements and so on. So as we understand, the technology, layered manufacturing technology initially had been brought with the idea of supporting the prototyping phase of product development. Basically, if we know, if we see about the phases of product development, we start with a set of customer requirements, or it could be the unique ideas. We go ahead with the concept designing, then further about the detailed designing, then analysis, and we try to optimize the design. Then we go ahead with the prototype. and we test the prototype, evaluate it, and then we'll go ahead with the actual manufacturing. So in this sequence of activities of product development, initially the prototyping phase consumed more time, as a result of which there had been delay in bringing the products right time to the market. So in this context, the layered manufacturing technology had been brought to support prototype development. Thereby, we can expedite the product development activities. That is how it had been brought. Next level, it had been taken for tooling and other aspects. We will discuss subsequently regarding those aspects. So as we all know, we are moving ahead with the time compression engineering, where we have several activities. If you see, there are two engineering approaches fundamentally. One is about sequential way, where activities try to go one next the another, and the another being the concurrent way of the activities. And we could very well see the advantage of this concurrent or simultaneous approach is that we'll be able to save time. Ultimately, the engineering efforts would be saved. Say, for example, with the layered manufacturing technology, the prototyping, tool making, and manufacturing phases have been made concurrent. As a result of which, it helps us in optimizing time and other aspects as well. So now there is a great need for this kind of time compression, especially we are now moving towards the fourth industrial revolution, which is all about the technological utilization and so on. So this kind of an scenario is vital. And then the basic process of layered manufacturing that all of us know. So in the pre-processing phase, we deal with the numerical modeling, especially in terms of developing the digital model. And we know pretty well for the this layered manufacturing, we'll go ahead with the solid model. Of course, the surface model also can help us. And we do have certain file format, especially we deal with the stereolithography file. And then we'll go further with the supports, depending on the part, whether it has an intricate structure and so on. Then we go ahead with the slicer, so which slice the part into various layers depending on the layer thickness, which is an engineering, which is a specification, important specification of our additive manufacturing machine. And we try to develop the prototype, so called the part, and then we go ahead with the post-processing, set of post-processing activities, wherein we try to remove the support structures, if so we have, or we will go ahead with certain post-processing activities in terms of secondary process, like enhancing the strength by means of woven curing, or maybe like we try to go ahead with infiltration and other secondary processing we do in powder metallurgy applications. That is depending on the need and depending on the engineering properties to be important and so on. This is how a general layered manufacturing process works. And there are several technologies, of course, other experts might have covered certain technologies, but I will be spending some time on discussing about the process which are relevant for 3D printing. So there are three processes which I would like to discuss as a part of my presentation. The first being fusion deposition modeling. Why I have taken this process the first, though if you see the chronology, stereolithography comes first, but depending on the applications we have with regard to the 3D printing, I would like to discuss about fusion deposition modeling first as a part of it. As we all know, it's an extrusion type additive manufacturing, wherein we have the kind of the raw material in the spool form, especially we have both model and support material as per this FDM process, and we have the heating chamber where the spool of raw material is being heated. We have certain heated arrangement, and then through the nozzles, the molten polymer gets deposited. It goes layer by layer. This is nothing but, you could see this red part is nothing but the overhang structure, which is the part to be created. And you could see the checked segment, which is nothing but the support structure to be built. And the entire movement will be governed with a mechanism as a part of it. Once a particular layer is being formed, the platform goes down, and accordingly the next layer formation happens and so on. This is the layer formation mechanics with regard to the FDM process. And it is for polymers. Mostly in the third revolution, we did a lot with polymers, maybe like ABS, PLA, and variety of polymers we could process in FDM technology. If you see commercially in the market, the open market, if we see, they call by the name filament fabrication. Fuse the filament fabrication they call. Okay, both mean the same. Either fuse the deposition modeling or fuse the filament fabrication. Both the terminology remains same, and their process mechanism remains same. It's based on the extrusion type process. It's a part. And majority of the printers, they are based on this FDM process because one unique advantage it has is it's a non-laser based process. One of the classification of this layered manufacturing technology is whether it employs a laser or not. It doesn't employ a laser, and corresponding laser optics didn't come into picture. So accordingly, the cost associated with the FDM process is less as a part of it. That's why if you see many of the commercial printers, they do go ahead with the FDM process. Of course, the FDM process has its own advantage as a part of it. It could process a variety of polymers, and it has the fabrication effectiveness and other aspects. And the applications ranges from starting from the conceptual design, then engineering analysis, tooling and manufacturing, and so on. So the application range is varied, and it supports to the possible extent certain applications which are required from the industrial perspectives as well. That's about diffuse deposition modeling. So the next process I would like to discuss is about the stereolithography process. As I mentioned, chronologically, stereolithography process marked the evolution of layered manufacturing technology, which all of us know. And this stereolithography process, the raw material, if you see, is in the form of a powdered liquid polymer, liquid resin. So here there will be a resin chamber, and the liquid resin will be loaded to the chamber, and we have the corresponding laser optics here. We try to use a kind of a UV laser, and the laser will be passed to the resin tank, and the laser will cure the resin.
Hello, sir. Hello.
Yes.
Sorry for this, sir.
Yes.
Sir, you're changing the slide, sir.
Yeah, I'm changing.
So it is not here not visible to see the slide.
Now I am in stereolithography process. Which slide is being
it is not in the, sir. It is not the slide is not changing, sir.
Okay, let me just check it out. Let me just stop sharing and then do it.
Okay, sir. Okay.
Just a moment, I'm sharing maybe. Could you see now?
Yes, sir. Yes, sir. Yes, sir.
Okay, so I will not go to the full screen mode, because if I go to the full screen mode, the display is getting the slide change. There is some delay and they couldn't see. So I'll keep in this mode and I'll proceed with my presentation.
Okay.
Okay. Anyway, I am now in stereolithography process. Let me show the slides alone, which I have done earlier, because of course we had discussion. I started somewhere with the impact of the this kind of layered manufacturing technology with regard to product development. We discussed, then we went ahead with the time compression engineering, where we could see both sequential and concurrent approaches, and the significance of concurrent approaches we discussed. And we had a discussion on the basic mechanism of this layered manufacturing process. We had discussion. Then, of course, I told there are several layered manufacturing technologies, and we discussed about the diffuse deposition modeling process. We understood the process mechanics, where the raw material is in the form of a spool form, and it is being fed to the melting chamber, and we have the heaters which heat the polymer, and through the molten through the nozzle, the molten polymer gets deposited layer by layer. So we discussed the process of layer formation in diffuse deposition modeling, and we discussed the advantages and applications, and now we are into the stereolithography process. As I mentioned, the raw material is in the form of a liquid resin, and we have a resin tank, and the UV laser is being passed on to the resin, and then the laser is used to cure the resin. It goes by a point-by-point approach to create a layer. The layer is created by means of the laser which is being passed to the resin tank. It goes by a point-by-point route, and then it creates a layer as a part of it. And once a particular layer is formed, the platform will be lowered, and again the laser will be passed, and the the resin will be cured. Accordingly, the layer formation gets completed. So depending on the number of layers as a part. Okay. Again, the type of laser being used is an UV laser. So there are different advantages for this lithography process, and it's a different as per ISO. As I mentioned, for diffuse deposition modeling, it's an extrusion type process. And the stereolithography process is called photopolymerization process. It's called VAT photopolymerization. Okay. And one of the unique advantage with the SLA process, it has good resolution as a part of it. There is good dimensional accuracy as a part. And here the the technology in terms of the equipment is slightly costlier because it involves a laser and the corresponding optics as a part of it. But the process has good dimensional accuracy. And in this context, I would like to discuss about the advancements in the stereolithography process. As I mentioned, one of the unique advantages it has good dimensional accuracy. Hence, it finds the scope in precise manufacturing, especially in terms of the micro and nano fabrication. There is a variant of stereolithography which had been brought, and it is being used as micro SLA as a part of it. Whereas when we see the other process, they don't comply with the requirement of the precise fabrication, and hence the stereolithography has good scope for this kind of an application. You see the micro stereolithography, the laser spot size and the layer thickness, they are of the order of 100 micrometer. And when the laser beam is focused to a spot size of about 1 to 2 micrometer, we could create the thin layers of the order of 1 to 10 micrometer. So in this context, it has very good scope in this kind of precise applications. Say, for example, in automotive and aerospace component industries, even in medical applications, it has very good scope. The reason being due to the advantage associated with the stereolithography process in terms of the very good dimensional accuracy is a part. So one of the variant of stereolithography which we discussed is micro SLA, and the second variant which I would like to discuss is about digital light processing, which is called DLP based printing. So if you see, DLP is a derivative of stereolithography process, but principally, though they are same, but the difference comes, one of the difference comes in the layer formation mechanics. As I mentioned, for the stereolithography process, it goes by a point-by-point approach and it creates a layer. Whereas in the case of a DLP process, it projects the resin at a single stretch and it forms a layer at a single stretch. So it is faster, relatively faster when compared with SLA. That is one of the difference of the DLP and SLA systems. And the second difference is nothing but in a DLP process, we'll be using the projector light source to cure the resin, whereas with an SLA process, we'll be using an UV laser. This is the second difference between the DLP and SLA process as a part. But DLP also has very good scope for, as I mentioned, for micro SLA. It finds applications in the defense, automotive components industry, electronics component industry, and in terms of jewelry fabrication, where the kind of precision is of the higher order, and even in medical implants, and in some of the surgical aids, the micro SLA and DLP also support as a part of it. So now the second process which we discussed, this SLA process, and we discussed the two of its variants, one in terms of micro SLA and the second in terms of DLP process. Okay. Now, having discussed about the SLA process, the next process I would like to discuss is about selective laser sintering, SLS process. And here, the raw material is in the form of a powder. And here we could see there are two powder feed cartridges. And these two powder feed cartridges will feed the powder to the deposition chamber. And once the powder gets deposited in this chamber, the roller will spread the powder uniformly across the deposition chamber, and the laser will be passed. Here the type of laser being used is a CO2 laser. The CO2 laser will heat the powder bed to a temperature which is just sufficient to fuse the powders as a part of it. Here only the fusion, the action of fusion happens as a part of it. And again, the next, the powder feed cartridges will feed the powder, the roller will spread the powder uniformly, and the laser will be passed and so on. So here the mechanism we need to understand is the layer is formed based on the action of fusion, because the powder bed is being heated to a temperature which is just sufficient to fuse the powder as a part of it. We are not going with melting, but we are going with fusion as a part. The type of laser being used is a CO2 laser. And as per ISO, this SLS process is called the powder bed fusion process, which has very good scope and very good applications in terms of metallic printing, which we'll be discussing through its variants as well as a part of it. It has very good scope, and the majority of the industrial applications. And if you see, one of the variants of selective laser sintering is a direct metal laser sintering, DMLS process. Principally, it's same, but we'll be dealing with the metal alloys in DMLS. And maybe like in the next variant is SLM, selective laser melting. There we will go to the actual melting range. In laser sintering, we are working for ahead of the melting range. That is in terms of heating the powder bed to a temperature which helps to fuse the powders. Batch in selective laser melting, we are going with melting of the powder, and ultimately we form a homogeneous melt, wherein we could work with the titanium, aluminum, and variety of metal powders, and it supports metallic printing. Because one of the important challenges, I think, but in trying to arrive at the mechanisms which could support this kind of direct manufacturing of the metallic parts, so which SLM could do as a part. So the direct metal laser sintering and SLM are the two variants of the laser sintering process. Okay, so now we discussed about the three principal process which are applied in 3D printers. That is fused deposition modeling, stereolithography, and selective laser sintering. And we discussed on the corresponding variants to understand the advancements in the field in terms of these processes as a part. Okay, now we shall, before we move ahead with understanding the trends of 3D printing, let us quickly go through the tooling aspect and the file formats for the layered manufacturing. Especially, we know pretty well in tooling, there are two approaches, one being direct and another one indirect. In direct approach, we'll try to fabricate the metallic tooling using this layered manufacturing technology. See, for example, through DMLS or SLM, I try to fabricate the metallic die. Okay, that approach is called direct tooling. Whereas in indirect tooling, we try to make a kind of a silicone rubber mold. Using the silicone rubber mold, we try to pour the metal, and then we try to get the metallic tooling. Likewise, that's we try to arrive at a kind of an intermediate tooling using layered manufacturing, and further we try to make the metallic tooling. That is how we do in indirect tooling, and there are certain advancements in direct and indirect tooling as a part. Then from tooling, as I mentioned, the layered manufacturing is being explored for direct manufacturing of induced parts, complex structures as a part of it. So that is being supported with the rapid manufacturing. Okay, the whole terminology which we had earlier, like rapid prototyping, now it got changed to rapid manufacturing, and further we are referring by the term additive manufacturing as per the ISO standard and so on. Next, while dealing with the file formats, we all pretty well know STL file is the preferred file format with this layered manufacturing. So in STL file, we have two formats. One is binary and ASCII file. The binary file is more compact, whereas the ASCII file is larger in size. But in terms of the... Yes?
Sir, you're in the which slide, sir?
Selective laser sintering.
Okay, sir. Okay.
Right. Of course, now you don't have some issue, I think.
Okay. Okay, sir. Okay, thanks.
So in terms of file formats, binary one is more compact, and the ASCII is larger file size, and maybe like in terms of the machineries, binary is more machine compatible file, whereas ASCII is not so as a part. And many contents which I'm discussing may not be there in the, each and everything may not be there in the slide. This is for the note to the faculty and scholar participants. Okay. And so now, in terms of the file formats, we are moving ahead with the additive manufacturing file format, AMF format as a part of it. So there are research being undertaken to bring out with compatible file formats with layered manufacturing technology. Okay, so having discussed about these concepts, let us move ahead with the trends of 3D printing in order to understand how the technology went ahead, because in the we utilized 3D printing to a greater extent in the third industrial revolution as a part of it. Let us try to understand and appreciate how the technology got stabilized under time, how it got proliferated into for diversified applications. Let us see. If you say somewhere in 1980s, we had the kind of the technology of 3D printing, which is brought in line with the stereolithography concept by Charles Hull. We could see the hardware and the corresponding software being used in those days as a part of it. Then somewhere in 1990s, we could see the kind of the 3D printer, which is in line with the fuselage deposition modeling by Stratasys. We could see the kind of the hardware and the interfacing software, which is in line with the CAD tools as a part of it. And this is how the 3D printing have started its journey. And in 2005, we could see the kind of the RepRap machine, which is nothing but self-replicating type machine as a part of it. That means the 3D printer can print certain parts of it. Ultimately, the idea is that we need to bring new printers from the one which is existing. So we try to explore the possibility of printing the parts of a 3D printer and creating new printers. That is the idea. But initially, when it had been explored, it was not possible to build majority of its components, but few of its components could be created using 3D printer. And it is of collaborative type printing as a part. And in 2006, we could see the idea of powder bed fusion, that is SLS process, which is being used for 3D printing as a part of it, especially in dealing with the metallic products manufacturing. And in 2008, we could see the kind of a RepRap machine, as I mentioned earlier, the self-replicating type machine, which can print majority of its components. So the capability got enhanced. A 3D printer can print majority of its components as a part of it. Okay. Ultimately, it can give rise to new other 3D printers. Then in 2008, the same time frame, we could see the kind of an idea of concrete printing, which had been brought into practice at Loughborough University, UK. Where the idea of the gantry type robo arm, we could see there has been a part of the 3D printer which can pour the concrete floor, concrete mix, it can pour as a part of it. Very precisely it can do. That is why we could see the 3D printers which are being used in construction type activities as a part. It's more interesting to note this kind of application. Then 2009, you could see the idea of 3D printers being used for some personal applications, especially the kind of the kids. You could see them. They want the toy of their choice. So what they do, they try to pick the digital file of their choice and they give to a 3D printer which can print the toy of their choice. It's a very excellent example for the customization as a part of it, because we know pretty well now we are moving ahead with the advanced level of customization in manufacturing. Okay. So this is a kind of, this is a very good example where this kind of customization is being very well witnessed in the context of okay. So this is a kind of, this is a very good example where this kind of customization is being very well witnessed in the context of the personal applications. Then somewhere in 2011, we could see the idea of 3D printing in food industry, especially when we visit the kind of pizza shops in pizza making. They try to pour the pizza floor, the pizza mix through these nozzles of the 3D printer. Very precisely, they pour the food floor. So it's very precisely it does as a part of it. So in the food industry, the implementation had been continuing. So now we could see the different technologies, as I mentioned, the extrusion type additive manufacturing for FDM and powder bed fusion is about SLS, photopolymerization in terms of SLA, like we have binder jetting and other processes. But the technologies which are relevant for 3D printing, we discussed earlier. Now you could very well correlate that the why I have taken into account these three processes for discussion. Let us now see the 3D printers market segment adoption curves. So across the time frame, we could see the 3D printers adoption. Initially, as I mentioned, it had been explored only for prototyping purpose. And the second branched application or the development is in terms of supporting tool making. And the third is about direct digital manufacturing, manufacture of induced parts directly. Then about the personal fabrication, and so on. So now we could see how the kind of applications of 3D printers have become diversified starting from prototyping, it has reached to personal fabrication, and ultimately it is going ahead in its journey as a part of it. So now from 3D printing, we are moving towards 4-dimensional printing, where we try to take into account the time as the fourth parameter, so that we could see the kind of shape memory materials and the smart materials are being utilized. So there way we can print the parts and they get self-assembled and so on. Accordingly, we try to do it. That is nothing but 4-dimensional printing, which is in research mode, but still we'll be able to see its applications more in the coming years as a part of it, like 3D printing. So the next, this slide shows the kind of the leading manufacturers of 3D printer. If you take, we have Ultimaker, MakerBot, Stratasys 3D Systems. Likewise, they have they lead in market in terms of the 3D printers manufacturing. Next, coming to the technologies, if you could see in this, FDM is having about 64% contribution of the 3D printers. Next, about the SLA and DLP, about 18 to 19% contribution. Then coming to SLS, about 11% contribution. This chart depicts that these three technologies lead in terms of 3D printing. That is how I took these three processes for discussion on their layer formation mechanics. We reviewed as they are very highly relevant for 3D printing, and of course we discussed their corresponding advancements as well. Next, if you see the kind of materials, PLA, ABS, polycarbonate, polyamide materials, those polymers, they have the applications more, and of course other polymers are also have compatibility with 3D printers. And we could see the 3D printers in different applications, starting from the automotive, aerospace industries, medical, implants making, biomedical applications, jewelry fabrication. Like this, the application we could see in the kind of the construction industry, food industry, personal fabrication. Like this, the applications are increasing more and more as a part of it. That's how it is more interesting to see the kind of the trends in 3D printers, so that it will give an idea of how the technology has got diversified in terms of applications, especially with regard to multiple domains as a part of it. Okay, so with this, now so far we discussed about the fundamentals of layer manufacturing, maybe, and we discussed about the technologies relevant for 3D printers. Then we went ahead with the discussion on the 3D printer trends, as well the materials, technologies, and the manufacturers, so on. So with this, we will proceed with some case studies for 3D printing. I would like to show one or two case studies to understand how, for what application we utilize this 3D printing, in which context, what challenges we had, and so on as a part of it. So the first study is about maybe making this kind of rotary switches, okay, where we could see this kind of switches in the panel boards. Their purpose is to read the current or voltage between the phases and to facilitate the phase changeover application. Majority of the components of the switch are plastic injection molded. So this for the switch, we went ahead with the kind of a product development project, wherein on the left side you could see the kind of the exploded view of the switch. So the mechanism is simple here. We have the kind of a knob or handle which can actuate the knob shaft, which in turn actuate the cams, which will make and break the contacts, and accordingly the switch works. And for majority of the components, we got the newer variants, the designs, especially in line with customer requirements, and especially through innovation, we tried with the different designs for majority of the components. For one of the component is being shown in the slide. And here we utilize the kind of a solid dimension based 3D printer. On the left, you could see the 3D printer. So here the raw material is in the form of a PVC sheet. Once it is being laid onto the chamber, and we apply a layer of glue, and there will be the trimming knife which can cut the profile of the component to be made, and there will be anti-glue pin which can remove the glue from unwanted areas. And accordingly, the next layer of sheet will be laid. The idea is that at the end, you'll be able to remove the anti-glued part, and accordingly, you'll be able to get the actual part for printing. And here one of the important aspects to be noted is nothing but the orientation of the part. Because earlier in that interfacing software module, the kind of the orientation we may have to decide, but now the optimal orientation is being indicated by the interfacing software. So we may be able to find out the optimal orientation, because if by mistake if you put a wrong orientation, it will lead to more material consumption, more number of layers will be created, it will increase the cost, time, and so on. And second thing is the thing, but now we have the concept for this optimal orientation, which the software module can indicate, and we can do certain optimization during the design phase. Say for example, I want to reduce the time for printing, or maybe like I want to optimize the product design. I can do very well here, and certain parameters could be optimized before I take ahead with the actual manufacturing. And on the bottom, you could see the kind of the prototypes being created using this printer. Here, the objective for us to develop the prototypes is nothing but to visualize the design. The customer wants to visualize the design. And second thing, we have a kind of a top tester in the company. So we could put the designs and we could test whether it's capable of withstanding the torque or not. So accordingly, the prototypes being made, we're capable of withstanding the engineering parameters. And for these two applications, we went ahead with the kind of the solid dimension printing, which it's a polymer based printing. We went ahead and we could fulfill this objective. So important aspect is nothing but which is technology to be selected in the context of additive manufacturing. We have several technologies. One, based on the application. Second, about the engineering properties to be fulfilled, and about the cost and other aspects you should try. So naturally, it involves multiple criteria. So you may have to take into account different criteria while selecting a right manufacturing technique, right technology for additive manufacturing. It's again, it's a challenge, but it's more interesting as a approach. So now I would like to show the second case study, wherein this case study is about developing the impeller and casing for a centrifugal pump in order to enhance the efficiency of the pump. In that context, we worked on with the project, and this is nothing but the activities we did. And these two are the designs of the impeller and casing for the existing pump design. So here we had a challenge to come out with the improvised designs for the impeller and casing. So as we all know, the pump design involves several parameters, and head and discharge being the input parameters. We may have to take in these input parameters, and then we may have to arrive at the new dimensions, the dimensions for the modified designs. So here, if you see the pump design, actually, as I mentioned, involves several parameters. We may have to take into account the head and discharge value, and accordingly, we may have to analyze the characteristic curves of the pump and the impeller and casing dimensions to be derived. But when we started with the project, it consumed more time in terms of computing the dimensions. Every time we need to analyze the characteristic curves, we need to compute specific speed and other parameters, and accordingly we need to arrive at. So in order to overcome this challenge, what we did is a kind of a software support we developed. But once I give the input parameters as head and discharge, it does the analysis and it computes the impeller and casing dimensions. So multiple times I'll be able to arrive at the parameters, and then I can, once I finalize the optimal parameters, then I can go ahead with the designs. Then the second challenge we had is nothing but in this design process, which is iterative, we may have to work on with several designs in order to arrive the best design. So in this, we went ahead with the parametric approach of CAD utilized, so that the solid modeler, once I define the chain of parameters in my base design, so accordingly when I change the input parameters, so this key chain of design parameters get changed on their own, and it generates the design. So I could generate my designs using CAD, and after arriving at the best possible design, then we went ahead with the analysis, being is the fluid component we did with the CFD analysis, and accordingly we checked the convergence of solutions and the optimal solutions we arrived at. And next we need to, we went ahead with prototype making. So in this context, we did with FDM machine. So on the top, you could see the STL file of an impeller. And the bottom, you could see the prototype of the impeller being fabricated. So here we did with an ABS. But if you see the actual material, it's a bronze alloy as a part of it. But here we went ahead with the FDM, and subsequently we did infiltration using the kind of the material powders, and we could enhance the strength. And once we enhanced the strength of the prototype, next we had the test rig in the company, through which we could test this impeller with regard to the properties. And once they fulfill the properties, they have taken further for the actual manufacturing of the components as a part of it. So here we could have gone with the metal printing, but still we went ahead with the kind of FDM and supported with the infiltration. We went ahead with the hybrid thing, and accordingly we could make and ensure that the design is fine as a part of it. So that's about the second study. So whenever we have this situation about selecting the technology, of course, we need to take into account the cost and other parameters, and accordingly we may have to decide on the right technology. But the compliance with the engineering properties again is very important. So the result through experience, we may have to arrive at selection of a right additive manufacturing technology. That's very important. So this is the 3D printer which we have in our additive manufacturing lab at our institute, and it's from Stratasys. And we should know the specifications of a 3D printer. Okay, it's first about the technology. It's an FDM process, material extrusion process, and about the material. The model material is ABS, and support material is also ABS as a part of it. And the build size is nothing but the maximum size of a part I could print using a 3D printer. So here it's about 8 by 6 by 6 inch as a part. And the layer thickness is about 0.254 mm. Very important parameters, the build size and the layer thickness. And of course, we have other parameters like specifications like size and weight and power requirements and so on as a part. Okay. And this is the interfacing software we have in our lab. Earlier we used the Catalyst, and later we moved to the GraphCAD. And through this interfacing software, once I import the CAD model as an STL file, I'll be able to specify the support structure. In the support structure also, I can specify the optimal one, because there are completely surrounding and like sparse different structures are there. I may have to arrive at the right structure as a part of it. And then I could go ahead with the usual procedure, and I have the slicer which could slice depending on the layer thickness, and accordingly I can make the prototypes as a part. These are some of the components we printed in our lab. One on the top left, we could see a medical gripper. One on the top right, we could see the kind of a guide vein runner. In the bottom left, we could see a kind of a femur bone in a medical application project. One on the left right, we could see a kind of a shaft using automotive application. Next, we worked on with an automotive mirror development for an automotive industry. These are some of the projects we did in our lab as a part of it. So before we go ahead with the second module for discussion, I would like to mention additive manufacturing is a key technology which is going to take a very higher magnitude lead in Industry 4.0, and there are a lot of advancements in additive manufacturing. And as I mentioned, some of the technological advancements, apart from that, we are moving ahead with the 4D printing. Next, we are working on the design for additive manufacturing. As we do in subtractive manufacturing, a design which is being made has to be manufactured. Keeping in mind several aspects, we explored in additive manufacturing how a design could be additively manufactured, for which there are different principles we may have to take into account, because there are several technologies, and the improving the feasibility of additive manufacturing through this DFM is also very, very essential. And the second important aspect I would like to mention is about the optimization. So generally in subtractive manufacturing, we may have done a lot of optimization, maybe the process parameters and other aspects. But here, we may have to work on with the topology of the shape. The topology-based optimization is very much essential for additive manufacturing as a part of it. Wherein industries, they work on a lot towards optimizing these kind of the structures, especially we need to work on with the lattice structures and the lightweight structures, which are very, very essential for automotive or aerospace component industries, including defense applications. So it's more interesting to explore these technologies. And even I would like to sincerely congratulate the organizers for taking ahead a right topic which has state-of-art relevance in the present manufacturing scenario as we are venturing into Industry 4.0. So taking ahead these kind of discussions And this kind of the research avenues is very, very essential as a part of it. And we may have to closely work with the industries as a part of it. We take into any account the industrial requirements. Accordingly, the technological development need to take place as a part of it. Okay, so this is the first module of my presentation. So let me see if there are any questions at this time before we move ahead with the second module. Okay, are there any questions from the participants till this stage?
Any questions from participants? Hello? Any questions? So what are the RPT systems you are using in your college, sir? Hello?
Yeah, so we have a 3D printer which is based on this FDM based, the polymer based printing we have, and apart from that we are creating certain facilities for metal printing also as a part of it.
Okay, sir.
Okay, any questions from the participants?
Hello?
Yes.
Hello, any questions, sir? Or we go to the next model?
Yeah, let me proceed.
Okay, sir. Okay, sir.
I'm sharing the content.
Okay, sir. Okay.
Just a moment. Dr. Manikandan, is my content visible?
Yes, sir. Yes, sir. Yes, sir.
Okay, let me put it in that this mode.
Okay, sir. Okay.
Is it visible now? Okay.
Yes, sir. Visible, sir. Visible, sir.
Okay.
Okay.
So okay, yes, let us continue with the thing.
Sir. Hello.
Will I be
Hello.
getting time till? Yes.
Yes, you can present. You can do the screen on presentation mode, please.
Yeah, that's what I tried.
Because it is very smaller. We cannot visualize that.
I understand, but there is a problem with the platform. Okay, I tried sharing in that. In that only we couldn't see in the full screen mode. That's the thing. I went with this mode for presentation. I'm trying my best to maximize the screen, but if I put in the full screen, there's a problem with the platform. I hope you are able to understand. Dr. Manikandan, is the content visible, isn't it?
Yes, sir. Yes, sir. Visible, sir.
Yes, let me proceed.
Enlarge that. Okay, sir. Okay.
Yeah, that's what I have enlarged because if I go in the full screen mode, there's a problem with the platform. I do not know. Okay, sir.
Okay, sir. Okay.
Let us not waste time in this.
Okay, sir. Okay.
So the second module of before that, Dr. Manikandan, will I be getting time till 1:20?
No problem, sir. No problem, sir.
Okay, because we started maybe like 10 minutes late, but still I would like to comply with time. By 1:20, I'll be able to finish.
Okay, sir. No problem, sir. Okay, sir. Okay.
Right. So the second module of my presentation is about Industry 4.0. As we had discussion in the first module about the 3D printing, and especially about additive manufacturing. Okay. So next, let us try to understand the industrial evolution before we go ahead with the actual discussion on the Industry 4.0 concepts. Okay, so the first revolution, it took place with regard to the mechanization, wherein we try to utilize the mechanical and steam power. And the second revolution is about electrification, where we had the concept of mass production supported with the dedicated product lines, assembly lines, and so on, supported with the electrical energy. And about the third revolution, which we presently had, is all about utilizing the electronics and information technology, ultimately to progress with autonomous manufacturing. So wherein we had the discussion on the 3D printers, we utilize the 3D printers, especially for making the polymer products, and we started with metal-based printing as well in Industry 3.0. And now in Industry 4.0, it's nothing but we will be focusing on developing a kind of a smart factory, ultimately utilizing the concept of cyber physical systems, Internet of Things, and other related technologies, including additive manufacturing. So ultimately, we try to develop a kind of a smart factory. Okay, we could see across the time frame, the level of complexity is getting increased as a part. So we need to the manufacturing technologies how to be supportive and how to be incorporated with the technologies in such a way that this kind of complexity could be taken ahead as a part. Next, we all pretty well know Industry 4.0 originated from the German industries, and in line with that, in US, from the context of US, they call by the name smart manufacturing. So ultimately, it includes several technologies like such as cyber physical systems, CPS, Internet of Things, IoT, Internet of Industrial Internet of Things, additive manufacturing, and so on. Ultimately, we move ahead with the development of a smart factory. So in smart factory, we try to take ahead with the digital twin, linking the physical world and the virtual world. How we need to interface these two extremities is one of the important challenge for us as a part of it. And over this Internet of Things, CPS has to communicate. A lot of interfaces are needed. The CPS has to communicate with the human. CPS has to coordinate with the machinery, and there should be certain interaction between the human and machineries and the human and robotic systems. Like it, a lot of interaction should be there as a part of it. But ultimately, if you see, the backbone for an Industry 4.0 system is all about the CPS, which forms the base. And we could see we need to enrich the system through powerful sensors, actuators, and artificial intelligence and other technologies driven by information technology. Ultimately, we need to focus on developing a smart factory as a part. Okay. So here, as I mentioned, CPS is the foundation for or the backbone for the Industry 4.0 system. So 3 C's are very, very essential in CPS. One is communication, second computation, and third control. And it is enriched with communication, information as a part of it. So here, what we try to do, the operations have to be completely monitored, it has to be coordinated, controlled, and it has to be integrated as a part of it. So definitely these kind of collaborating computational elements which have to be designed in order to control the physical entities as a part of it. So CPS has a greater role in terms of coordination, in terms of interface with the human and machinery, ultimately, along with robotic systems, in order to ensure that the digital, the kind of smart factory is able to run as a part. So we could see the kind of the scenario of the present factories which we have, maybe like in line with the 3.0 version, wherein the systems have been incorporated with flexibility. And of course, we have the robotic systems which have to communicate and coordinate. The kind of flexibility and versatility we may have to increase a lot as a part of it. Okay, so definitely the kind of systems we develop, say for example, the robotic systems, sometimes they may have to be autonomous in one sense. And also they have to be collaborative in another sense, coordinative in another sense as a part of it. Likewise, we try to enhance the versatility. We could see the kind of the workstations, and we may have to deal with the completely customized manufacturing as a part of it. And we may have to work on with the fully flexible and integrated system. We could see the kind of the coordination between the robotic systems and the workstations accordingly. And the CPS has a key role in coordinating with these elements ultimately, so that we'll be able to make the smart factory to be configured and reconfigured in line with the changes that happens in the manufacturing systems. Okay, so now if we could see, there are several principles governing this kind of an Industry 4.0 system. The first one is about interoperability, wherein it is the ability of CPS and as well the human and the smart factories, they may have to coordinate and communicate with each other, for which they need IoT and iOS, through which they will be able to communicate and coordinate with each other. Second is about virtualization, wherein we try to create a virtual version of the smart factory, and of course it has to be supported with the sensor data and the simulation models as well. Next, about decentralization, wherein the CPS ability, it has to be supported, it has to be provided with the decision-making ability on its own, like autonomous decision-making is very much needed as a part. Next, about the real-time capability, where we may have to completely collect and analyze the data very effectively as a part of it. Most likely, we'll be dealing with the big data as a part, and for which we need to have the robust analytics in the sense. Next, about the service orientation, wherein we try to take into account the service aspect through iOS and other means. Next, about the modularity, where the smart factories, they may have to be modular in the sense they may have to adapt to that of the requirements in line with the changing modules. They have to be adaptable. That is most important. So these 6 design principles are governing an i4 kind of a smart factory as a part. Next, if we could see the digital twin, wherein we have the physical world as well the virtual world, also called the digital world, they have to be interfaced and supported in several functions like product design, production planning, production engineering, and so on as a part of it. For which we take the help of the simulation and lifecycle management tool and manufacturing execution system and automation and so on as a part. So here we could see the completely value chain is digitized and it is completely integrated as a part of it. So this kind of an linking this physical world and the virtual world is an important challenge for the Industry 4.0 or the smart system. Next, it is more interesting to see the kind of skills requirement, because if you see the skills required for the Industry 3.0 system and asset of the Industry 4.0 system is slightly different in the sense Industry 4.0 requires a certain unique capabilities. If we note some of the unique capabilities, one is about the emotional intelligence as a part of it, because we have to bring about the kind of complete innovation in terms of product development, materials development, process development, a lot of innovation we have to bring about. And second important skill, if you see, the cognitive aspect, because here we may have to think multiple concepts simultaneously as a part of it, and then the kind of the ability to be acquired in dealing with these multiple concepts to arrive at the best one is more interesting as a part of it. So the kind of the skills requirement will help us to prepare even our students as a part of it, because they are going to work with the typical Industry 4.0 system. So accordingly, when we are discussing about the concepts and other aspects, we may have to provide the insights so that these kind of skills will be able to impart to our students. Next, if we say about the need for Industry 4.0 system, so here we need to transform the kind of conventional machines to be of self-aware or self-learning machines. So here we try to take the help of the machine learning, deep learning, and other technologies in order to ensure this kind of a transformation. And second, we try to create a smart manufacturing platform in order to facilitate the industrial network, the applications. Then we may have to do the real-time data monitoring, data tracking, data analysis is very, very essential. So the product recognition systems and other systems are also very essential as a part of it. Next, if you see the kind of benefits of an Industry 4.0 system, here we will be able to make the manufacturing enterprises to be flexible, and they have to be made reactive to the changes in the market condition, and we may have to enhance this innovation speed, and we have to find long-term solutions for the problem. We need to have a long-term vision, and of course the productivity aspect is also there, and the collaborative pattern of working, and the more innovation opportunities. So if you see some of the classical questions which comes into picture with an Industry 4.0 or smart system, whether the kind of regarding the job opportunities. Actually, the opportunities are more in the sense, but the skills requirement is different. That's what I have shown in one of my earlier slides. What kind of skills are needed for an i4 system? And second thing, the kind of the learning aptitude or the kind of the innovation-oriented thought is very, very essential as a part of it. So such opportunities which we create that will help the kind of employees to think from different perspectives is very, very essential. So here we may have to take into interaction between the complete materials, product and process phenomenon as a part of it, and the unique solutions have to be brought about. And of course, here it creates the kind of profitability and other aspects. And here we'll be focusing on higher levels of flexibility and agility. In the sense, the system will be more versatile. It has to be highly responsive to the changing requirements as a part. That is, these are very, very essential as a part. Then if we try to see the definition for an I4 system, okay, the one on the top which I have given is a widely referred definition. Let us try to understand the definition. So here it tries to create a smart factory where it tries to bring the several technologies like big data analytics, Internet of Things, additive manufacturing, maybe like cloud-based systems, robotic systems, and so on, even including additive manufacturing. Likewise, variety of technologies are being implemented in order to form a CPS, cyber physical systems, as well as the human equipment interface. That interface we are creating is very, very essential as a part of it in order to contribute towards a sustainable system. So if we take a sustainable system, it will have a three-dimensional aspect. One is on the environment, second economy, and third society. In all these three dimensions, the kind of benefits need to be realized as a part of it. So that is more essential as a part of it. Let us take a very obvious example in order to understand how they have mentioned these three dimensions for a sustainable manufacturing system. Let us take the context of additive manufacturing. It's one of the key technology for an Industry 4.0 system. We are working on with optimize the structures. So once I optimize the structure, naturally the environmental impact, the CO2 emission will come down, which is about environmental dimension. Once I'm optimizing the design, naturally the cost reduction will be there, and accordingly we'll be able to have the profitability and other aspects from the economical aspect. Then about the societal thing, we are creating opportunities. We are providing a very good learning environment, and that will improve the work life of an employee. Likewise, if you take any technology, it will contribute towards these three dimensions. That is why it's very much noteworthy to refer this definition, which is a comprehensive definition for the Industry 4.0, which shows the technological integration to arrive at what kind of an interface, and ultimately how it will get reflected in the three dimensions in order to contribute to a sustainable system. That's about Industry 4.0. So there are several technologies for an I4 system. Let's spend some time on the technologies. So the first being CPS, as we discussed earlier, it has a system in order to control the computational elements, in order to have a complete control over the physical entity. Here we try to collaborate different computational elements to control physical entities. And here it is being supported with the data collection, data analysis, and it forms a very good interface between the human equipment, and ultimately it tries to form the backbone. There's a kind of a concept map which shows the various entities like the sensors and actuators, feedback systems, modeling and analysis systems, validation and verification systems, and the kind of applications in various domains. This concept map comprehensively shows the various elements of a CPS. So the next technology is about big data analytics. As I mentioned here, the kind of the data collection, data analysis, and deriving the patterns, trends, inferences is very, very essential as a part of it. But the kind of data we are going to operate and handle is a big data. So the term big data denotes not only about the volume of data, but also the variety of data, different forms of data, and other aspects. So here, if you see this scenario, we'll be having a kind of, we need to always find out the new solutions to a kind of new kind of problems we may get as a part of it. Then we could see how robust or how advanced the analytics should be in order to deal with this kind of the situation. And the data analytics is one of the key aspects of any manufacturing system. Of course, it holds good even for an Industry 4.0 system which deals with the big data. So the next technology for discussion is nothing but a horizontal and vertical integration. If we take a horizontal integration, Here we will try to establish partnerships among various stakeholders, and ultimately we try to form partnerships even with competitors and other firms, because I have certain core competence, my partner has certain core competence, we are taking ahead with the business venture and so on. Next, if we take the kind of a vertical integration, all activities, majority of the activities, they try to utilize the in-house competence, like starting from product design, product manufacturing, distribution, and so on. They try to utilize the in-house competence. But if you see, in Industry 4.0, both the integration are needed. Horizontal integration is also needed in terms of finding partnerships, and vertical integration in terms of the in-house capabilities is also needed. As a part, ultimately, we could see there are different technologies which can support, like lifecycle management tools, and maybe like big data and IoT, iOS also support us as a part of it in order to take ahead with this horizontal and vertical integration. Okay, next about additive manufacturing, as we had lengthy discussion on additive manufacturing as a part of it, and as I mentioned here, there are several technologies. Now we are moving ahead with the advancements in terms of metal printing and other aspects, especially to deal with this kind of the lightweight structures, complex geometries, and so on as a part of it. That's where I mentioned about the optimization and other capabilities that also to be focused as a part of additive manufacturing, because it is going to be the technology which is going to lead, and many of the conventional manufacturing systems are going to get transformed through this additive manufacturing, and it is going to take a lead in industrial developments as a part of it. Next, about the industrial Internet of Things. So wherein here we try to utilize the smart sensors, the smart actuators, ultimately in order to leverage the kind of the challenges which may have to take ahead as a part of it in order to facilitate better decisions. So here we will be having a lot of integration with through the sensors, actuators, and the communication mode and other, including robotic systems. In order to have a complete coordination, we could see here a kind of a draft idea of an industrial IoT, wherein we could see the kind of robotic systems, machine tools, the sensors, actuators, the kind of the processors, the communication protocols, because here the communication protocols are also very, very essential as a part of it. Okay, so beyond TCP, IP, and other protocols, a lot of protocols like IEEE based and ZigBee, and a variety of protocols are being taken ahead, including the product recognition or other schemes as a part of it. They have to be supported in order to execute the challenges of this kind of a smart factory. Next, about the augmented reality system. So here in augmented reality system, we try to provide an interactive experience of the real world, wherein we try to utilize this kind of the AR technologies, maybe like incorporated with the applications. So let's say, for example, I have a kind of a machine tool. If you want to see the complete history of the machine tool in terms of various breakdowns, or maybe like various the kind of downtime issues which have happened, how they have rectified, instead of referring to kind of the history codes, the manual history codes, the complete data will be available through an AR system. We'll be able to visualize the complete maintenance aspect of the machinery, and here we'll be able to supported with the cloud systems as a part of it. Even say, for example, some of the kind of the production based parameters, and second thing, the maintenance based parameters also could be monitored from a remote location. And this kind of AR systems are very well supportive of this kind of digital mode of operations, and they coordinate in a very big way in order to ensure the workplace safety as well as the operator safety as a part of it. And it also provides the complete mechanism of various machinery and equipment will be able to sense as a part of it. So it gives us a very fair idea of about the different technologies that happen, and this kind of AR systems are also very, very essential in monitoring many of the maintenance and quality parameters as a part of it, because we do have multiple machine tools, and they could be even operated and monitored maybe from the remote location, and this kind of AR systems also support us. But AR systems need to be supported with the Internet of Things and other cloud-based applications as a part of it, which will help a lot in taking ahead these kind of challenges as a part. So this is about the kind of Industry 4.0 system. So ultimately, we are moving ahead with the kind of a smart factory as a part. So, so in this regard, the kind of challenges we have and the kind of the applications are diversified as a part of it. So we have a kind of a great role in taking ahead this kind of systems for the implementation as a part. Okay, so this is about the Industry 4.0 system, the second module of my presentation. So are there any questions till this stage from participants?
Hello, any questions, participants? Hello? Any questions, sir?
Are there any questions from participants?
Hello, sir. Hello.
Are there any questions? Dr. Manigandan?
Yes, sir. Yes. Hello, sir. Can you hear my voice, sir? Hello?
Okay, I'm trying to share a video file. You just, I'll share, you just tell whether you're able to see the video file.
Okay, sir. Okay.
Technologies are changing the world.
Could you see the video file, Dr. Manigandan?
Yes, sir. Yes. Yes.
Okay. So it's a kind of an Industry 4.0 implementation video. Let us refer to the video.
The future of car manufacturing is also changing in a similar way. In fact, the next batch of innovations is so extraordinary that experts are already declaring the dawn of a new industrial era, Industry 4.0. So what does manufacturing look like today? Traditional car production involving hundreds of identical vehicles lined up in a row no longer exists. The options available to customers are now so vast that each car becomes a unique and individual object. Cars are now manufactured to order. Data makes its way from the customer's order to the Volkswagen Group's systems and then to each individual section of production. A car consists of many thousands of individual parts. The press shop processes blanks for the bodywork. In the body shop, the car is baptized. In other words, it's given an RFID tag that can track it via radio frequency. This establishes which car body belongs to which customer order. The paint shop also receives information from the system world. In sequencing storage, the cars are placed in an optimal order for assembly. From here, information is transmitted to suppliers and pre-assembly as to which part is required when and where. In final assembly, the finished car emerges. The Volkswagen Group manufactures its cars using state-of-the-art technology, but development and innovation never stop. What does the future hold in store? Today, everybody is talking about Industry 4.0. It is a term used to describe a variety of innovative production processes. But what exactly does it mean? The Volkswagen Group has been shaping the future with groundbreaking projects for many years. Here are some recent examples. Digitalization. The digitalization of all elements of production is essential for a new era in industrialization. Everything is given a virtual likeness in the system world. The result is an Internet of Things. Example, 3D printing. Pressing tools are no longer shaped in a laborious manner. Instead, these tools can be made from steel granulate in a 3D printer. It's a technology that opens the door on completely new possibilities for design, with a level of precision unknown until today. Example, human-robot cooperation. In the past, protective grids separated robot arms and employees. In the future, employees and robots will work increasingly hand in hand. This is made possible by new security sensors. Robots take on especially monotonous and arduous activities. Today, robots already play a part in contributing to ergonomic workplaces at the Volkswagen factories in Chemnitz and Salzgitter. Example, big data monitor in logistics. The big data monitor enables for the rapid visual processing of data from the 1,200 suppliers of the Audi factory in Neckarsulm. Where are the potential bottlenecks? Where is the greatest need for action? This data is now easily accessible at all times. The intelligent factory of tomorrow paves the way for efficient and cost-effective production unlike ever before. Industry 4.0 also means brand new opportunities for employees. The Volkswagen Group has already begun actively preparing its workforce for the future. The world is changing, not only in the automotive industry. Everything is in motion, and the Volkswagen Group provides the technology that moves the world.
Okay. So now from the this presentation, the video file, we could see the Industry 4.0 implementation activities in Volkswagen Group. Prior to that, they have shown the complete sequence of manufacturing activities involved in the car manufacturing, and they mentioned how they have gone ahead with the Industry 4.0 implementation, especially in terms of complete digitalization, wherein we could see the powder bed fusion additive manufacturing technology, the kind of the robotic system, how the robot is coordinative and responsive in line with the kind of the interface between the robotic system and the human, we could very well see, and big data analytics, how it is being deployed, and the kind of RFID based mechanism, product recognition mechanisms, and the Internet of Things, those kind of applications. So it's an excellent video which clearly shows the Industry 4.0 technologies being implemented. Okay, so having discussed about the additive manufacturing and Industry 4.0 for the discussion today, okay, so now let us see any questions from audience, from the participants.
Any questions, sir? Hello. So the Industry 4.0 is implemented in our country, sir. In any
Yeah,
yes.
many of the industries have started implementing Industry 4.0.
Oh. In
Okay,
MNC
technology integration, yeah, it has started implementing. They have started implementation.
Okay, okay. Any other questions, participants? Okay, sir. Okay. So if you want any questions, you can see that website, SAR website. It is in the Dr. S. Vinod NID Trichy. If you see that, you can also chat your questions. Thank you, sir. Hello.
Okay, Dr. Manivan, 1 second. Okay, I have a few things to be told before we wind off.
Okay, sir.
Faculty and scholar participants who are in this participating in this STTP. So from any STTP program or faculty development program, the kind of the discussions we take ahead, definitely we should take ahead in terms of offering similar courses at our institute. Maybe you may be offering similar courses, or you may intend to offer new courses. So definitely kindly take ahead offering similar courses for the students, and to guide students in these student projects, especially in these state-of-art technologies, and to explore about the industry-oriented projects, because some of the problems which the industry has, some kind of solutions could be derived from the projects, and some of the technologies which we develop, we can approach the industries for taking ahead the implementation. So in this context, the kind of takeoffs from these programs should help you, and maybe any kind of queries or suggestions you can write mail to me. And I thank you all for the patient listening, and I would like to thank Dr. Manigandan and other organizers for inviting me to deliver this lecture today. And a special mention to Dr. Manigandan, because he had taken efforts from the beginning very effectively. He communicated with us, made all communications very appropriate as a part of it. Thank you, Dr. Manigandan, and best wishes for all for taking ahead with this STTP. Thank you and have a fine day.
Thank you, sir. Sir, your session was so nice. I hope all the participants are enjoyed and understood the concepts very well. Thank you so much for sharing your knowledge, sir. We are
Okay.
very grateful to you and look the time out of your busy schedule. Thank you for your enlightening speech and enthusiastic participation. Once again, thank you so much, sir. Thank you, sir.
Okay. Okay. Thank you, Dr. Manigandan. Okay.
Thank you, sir.
I'm leaving the meeting. Okay. Thank you.
Okay. Thank you, sir. Thanks.
Okay.
Next session will start at 2:15 p.m. in the same link. Thank you, sir. Thank you. Hello?
Thank you.
Can you hear my voice?
Yes,
Thank
sir. Yes. Audible. Thank you.
Okay, sir. 2:15 we can join, sir. Okay.
Yes.
Sir. Thank you, sir.
Please share the feedback link, sir.
Feedback, sir. I will join. I will send. I will send, sir. I will send.
Yes.
Okay. Okay.
Thank you.
Thank you, sir. Thank you. Hello, good afternoon, sir. Hello. Good afternoon. Sir, Abdullah, sir.
Good afternoon, sir.
Joined, sir. Okay. Sir, shall we start 2:15, sir?
Yeah, sure, sir. No problem.
Participants are coming, sir. Okay,
Okay,
sir.
sir.
Okay, okay. Hello, sir. Abdullah, sir. Hello. Abdullah, sir. Hello, Abdullah sir. Hello. Hello, Abdullah sir. Sir, Abdullah sir. Hello.
Say yes, sir.
Sir, you will start, sir?
Yeah, sure, sir. No.
Okay. Good afternoon to all. It is immense pleasure to introduce our resource person, Mr. J. Abdullah, in this afternoon. He is working as a chief technical officer in CAD Solutions Private Limited, Coimbatore. He completed his ME Aeronautical Engineering. He is a specialist in FEA and CFD. He was a research associate at IIT Madras Ocean Engineering Department for a BHL funded project earlier. He has a total experience of around 10 years. He has effectively implemented CE software at numerous R&D centers. Now he is going to take a topic of reverse engineering using SolidWorks. Sir, please, sir.
So, thank you, sir.
Oh.
Good afternoon, everyone. So, hope I am audible and I am
Yes,
loud
sir.
and clear.
Yes, sir. Audible, sir. Audible.
Yeah, thank you, sir. Thank you for
Oh,
the feedback.
yes.
So, hope already you have seen different topics. So, related to additive manufacturing. So, the file formats and what can be done. So, what are the process, everything we have discussed. So, today in my session, I'm just going to give a hands-on. So, how we can do some reverse engineering activity using SolidWorks software. So, that's the agenda for today. So, whenever we talk about reverse engineering, so we always think about optimizing some existing models. So that's where when we think about, mostly we think about the reverse engineering terminology. So when we talk about reverse engineering, there are a lot of scenarios are there. Say whenever we have some real-time model, so we need to do reverse engineering, or we need to develop a new model. So based on the existing model, or we can say it as a component. So if it is the scenario, so generally what we will do means, so we will scan the existing model. So based on the scan data, we will go for 3D model creation, then we will modify the designs. So that's a general scenario. So we start with the existing model, we scan it, then we go for converting the scan data into a CAD model. From CAD, so we can able to get a parametric design. So we can modify the design, then we go for a new optimized design. So this is the one scenario. If you take another case, say for example, I don't have a real-time component or real-time model. I don't have any physical component or anything, but I have an image. So I want to create a model. So based on the existing image alone. So this is another scenario. So that means we need to develop a model from a image alone. And the third scenario will be, so if we consider an industry perspective, 20, 30 years back, most of the industry, they prefer creating design using 2D tools alone. Say, for example, we have a 2D data. From the 2D data, I want to quickly create a 3D design. So this is the another scenario. So these are the general scenarios as 3 occasions where we are using a reverse engineering. So reverse engineering nothing but so developing a model from a existing data. So if we have a real-time component means we can scan it, or some occasion we will have only an image. If we have an image means we need to recreate a model from that image perspective. The third scenario will be, so in some occasion we have a 2D data. So instead of scanning an existing prototype, since we have all the dimension in a 2D format, so we need to create a 3D design using the 2D data. So these are the 3 scenarios when we talk about a reverse engineering. So all these 3 scenarios can be easily approached using SolidWorks. So that's what we are going to discuss today. So just a minute, I will share my screen. So hope my screen is visible to everyone.
Yes, sir.
Okay, thank you. So I'm going to start with the first scenario, like, or maybe I can just open the thing. Okay, as I discussed about the first scenario. So we need to do a reverse engineering from
So
the
keep a full
real-time
screen,
object.
sir. Hello, sir.
Yeah,
Full
yeah,
screen,
sure.
full screen, yes, sir.
Okay. Actually, this is 1 or 2 slide. That's why I just kept it at the
Ah,
normal view.
okay, sir. Okay, okay, sir. Okay.
Okay. So first we will discuss from the scenario 1. That means we need to do a reverse engineering from a real-time object. So as we all aware, whenever we have a real-time object, we can scan the real-time model. So while scanning, we will get the float points. So earlier they use a CMM to measure the position of a points. Then based on that, they used to create. So nowadays it becomes very simple. So directly they are using some scanners, even handheld scanners are there. So they can scan the entire component. So all the things, all the overall object will be captured as a points, float points. And even in some scanners, so those points are directly converted into a mesh data, so like a triangles. So that's why I mentioned about a polygonal mesh. So these mesh data can be directly converted into a CAD. So this is the overall process when it comes to a real-time object. So how SolidWorks helps in that perspective means, so whenever we have a mesh data, so generally we call it as a mesh data or a graphic data. So this graphic data doesn't contain any area or a volume or any properties. There won't be any mass properties or kind of thing. So if I want to get all this information, obviously I need to convert the scan data into a CAD model. So that's where the softwares are using. So that's why in below I have mentioned about this process. So there is a scan part. So whenever we are scanning, so the object will be captured as a point. So that has to be converted into a mesh. That's why I mentioned convert to polygons. So these 2 things can be now easily done through a scanner itself. So converting from points to a polygons. So we will get an output in terms of polygon or a mesh data. So generally these mesh data, the common format will be STL format. So STL is not a format only used for additive manufacturing alone, because we all aware whenever we want to go with the additive manufacturing, we generally convert our CAD data into a STL files. So STL is nothing but it convert our CAD into a mesh data. So from the scanner, we obviously get the scan data. So our main work has to be, we need to convert those mesh data into a surface. From the surface, we need to develop a solid model. So this process, so creating surface and adding details or converting into a solid model. So that is the main thing. So for that, there are some processing software also there, but instead of going with some processing software, so now we have most of us aware about the SolidWorks for a CAD. So we can use the same CAD tool for this processing also. So that's what we are going to do now. I'm just going to give an example. So how this thing can be easily done through a SolidWorks tool. Okay, let me open a SolidWorks. So whenever I want to open a STL file, so we no need to go with the import kind of thing and all. So directly SolidWorks support most of the neutral file format. So directly we can open a
Hello, sir.
STL file.
Sorry for this one, sir.
Yeah.
Sir, voice is very low, sir.
Sorry.
Your voice is very low. It is.
Okay, sir.
It's
No
very,
issues. Am I audible now?
now it is clear, sir. Now it is clear.
Okay, sir. No issues. I
Okay,
can
sir.
manage.
Okay.
Sorry for that, sir. Okay.
Okay, sir. Okay, sir.
Okay, I'm going to show a simple example. So how we can convert mesh data into a solid model. So obviously, whenever we are talking about additive manufacturing, it is all about the non-conventional manufacturing. So we do reverse engineering to change the design or to modify the design. So whatever design we are doing, obviously we will go with the additive manufacturing or for a prototyping. So that's what we are going to see how SolidWorks is going to help. Okay. So as I mentioned earlier, so if I want to open STL file, that can be directly opened in SolidWorks environment. So let me open a STL file. So here I have a STL model. So the file format will be in STL. It's in mesh data only. So I can just select it and open. So if you see this mesh data, so these triangles, these are the things about mesh data. So our model will be discretized as a polygonal shapes or as a mesh data. So if you see on the left hand side in the feature manager, we can able to visualize as a graphics body. So graphics in the sense, it's just a representation. So there is no surface or there is no volume, or volume, or you can say it as any properties like mass properties. So nothing will be there. It's just a simple graphics body. Just it shows the visualization. Okay. So we are able to visualize only a component kind of thing. But if I want to go for a manufacturing, so obviously I need some solid model. Once a solid model is there, easily we can took it into a CAM software and we can generate all the process or all the steps. Or even once I get a solid model, if I want to do any modification, if I want to remove some material, or if I want to add some designs, we can able to easily do only in a solid body. So converting a mesh data into solid body is very easy in terms of SolidWorks. So earlier, there is a conventional process. So whenever we have a mesh data, obviously first what we need to do means we need to convert all the polygons into surface. From the surface, we need to go with a solid model. So that is a general scenario. But from the recent versions and all, so SolidWorks has a very good option to support these kind of reverse engineering. Say, for example, I have a graphics data. I want to directly convert this graphics into a solid model or a surface model. Then what I can do means simply I can right click on it. So directly I have an option. So the best part about a SolidWorks is user interface. Whenever we are selecting something, automatically SolidWorks suggests you a relevant options, what we can do with the selections. So here I have a mesh data. When I select and right click, automatically it shows them options which are relevant to convert mesh body into a solid body. The first thing is convert mesh body. So we have a graphics data. So we want to convert into a body. Either it may be a surface body or a solid body. So if you want to convert a graphics data, simply I can click on this option. So automatically I can give just OK. So all the graphics will be converted into a surface model. See here, I got a surface, and here also I had a surface body. But obviously, when I want to go for a manufacturing, I need a solid body. But here I got a surface body. So that's not an issue. So generally, whenever we have a closed environment, so automatically while converting, it is going to convert it into a solid body. But in this scenario, just to show you, so there is some openings are there in the scan data. Because whenever we are scanning, so there may be chances of some data losses. So in that data losses region, so we don't have any surface formation or any polygons. If that is the case, so how we can modify? How we can modify the scan data easily to create a solid? So that's a major thing. So if you take this mesh data, there is a small opening here in this corner. So you can able to visualize the opening here. So rest of the things are normal. It's a through hole. But only here at the corner, since it's a filleted corner, so these areas are not captured properly. So without patching this, I can't go for a solid model. So for patching, what we can do means, so SolidWorks has a lot of surface option. We can use some surface option to fill this region. That is a one perspective. But still, okay, I'm not familiar with surface, but I want to remove this hole. I want to patch this hole. So if I want to do like that means, so there are some easy ways also there. So only thing is we need to select that hole, right click, we can go for option called delete hole. By using this option, automatically SolidWorks will patch that region. So simply I am giving a delete hole. So see here, once I give a delete hole, so automatically those hole will be patched. So I can go with OK. So those holes are patched. So now my model becomes a completely closed model, but still it is in a surface. It's in a surface body only, but that's not an issue. So once we got a completely closed surface, so easily we can convert those surface into a solid body. So if I want to do that, so here I have an option called thickness. So I can use a thicken option in the surface command manager. I can select the body, and instead of giving thickness, so if it is a closed surface, if I want to create a volume, so there is an option, direct option, create solid from an enclosed volume. So simply I can select that object and I can go for OK. So once I give that option, directly our surface body will be converted into solid body. So we can see it here. So that's how simple it is. So whenever we have a scan data, if we want to create a solid model, so easily we can convert like this. So once we got a solid body, so it contains all the information. Even if I go with a sectional view, so I can able to section my model. So I can section and I can visualize my internal regions. But this cannot be possible in graphics data. So this is what the advantage of the tool. So from the scan data to the end of solid body. So now if I want to measure any mass properties or something, easily I can apply some material and I can check the mass properties. So that is for our understanding. Whenever we go for a prototype, we need some information. So those things and all directly we can get it here. And also once we got a solid body, if I want to have a manufacturing drawing, we can do some drafting and all. We can generate some orthographic views and we can get some manufacturing ready 2D drawings. So this is what about the first scenario. So using SolidWorks, so we can open a mesh data and we can convert that mesh data into a solid bodies. Maybe I can open another model. So these kind of reverse engineerings are largely used in a medical side and all. So to develop some implants, so like that, they are scanning the data. So again, here I have a scan data, a arm. So apart from directly converting mesh into a solid body, so we can do some decimation also. So decimation is nothing but, so we all aware, like whenever we have a large number of points, we can achieve a high quality. So mesh data will be very perfect based on the number of scan points. But in some occasion, if we have a more number of scan data, so it will be complicated to work on our systems. So our system memory won't support to work with the large cloud data points. So if I want to simplify the mesh data, I want to simplify it. So I don't want more accuracy. I want to have a rough model. So if I want to simplify the mesh, so that also can be easily done in the SolidWorks tool. Say for example, this is containing some set of some cloud points. So I want to simplify. I want to reduce the set of cloud points. Then what I can do means I can go with the mesh decimations. So for decimation, simply again, I can right click on the graphics data and I can go with the second option, decimate mesh body. So I can choose the decimation. So by default, this ARM contains, this scan data contains around 1,44,000 meshes. So the facet in the sense each a polygon shapes or triangular shape. So if I want to simplify so that I can easily work on my system. Because if I have a large number of cloud points, it takes a lot of time. So obviously we always want some more accuracy, but for initial stage, so I'm not need any accuracy, but I need some rough model for my prototype alone. So if I want to reduce the number of elements, then what I can do means I can go with the decimation. Here I can control the percentage. So I want to reduce a 20% of element count. So if I go with it means automatically the number of mesh data will be facet will be down to 1,15,000. So by default it is contained 1,44,000. So if I reduce the cloud points, say for example I want to reduce it by 35%, automatically the data will be reduced to less than 1 lakh. So simply I can go with calculate. So now we can observe the difference. So compared to the earlier density of mesh and current mesh. Actually, these are some simple files just to show in real time, even a single scan data will be larger than 1 GB or 2 GB file will be there. So it contains some large number of phases and all. So at that time, it'll be complicated for us to work on that model. Whenever we rotate or we do any operation, it will take a lot of time. So our system may get hang. To avoid this, if I want to get some prototype, then later I can correct the dimension. So in that occasion, I can go with these kind of decimations. And even now itself, we can see the difference compared to the previous one and current one.
Hello, sir. Hello, sir. Hello.
Yeah.
Hello.
Yes, sir.
Sir, the voice is
Sir, please,
some
sir.
disturbances. The voice is some disturbances there, sir. Voice disturbance. Hello.
Is it okay,
Abdullah, sir.
No.
Hello. It's clear.
So am I audible now?
Hello.
Hello, sir.
Yes, sir. Yes, sir. Now you speak. Now you can speak, sir. Now you can speak. Hello.
Okay, no issue. I'm just waiting for it. The decimation is happening in the background. So just software is processing our request. So I just want to reduce the number of scan data, scan points. So just almost 90% is done. Okay, fine. So if we check now, so automatically the phase and counts, that is the polygon counts are drastically raised from 1,44,000 to 93,000. So now we can see the difference in the scan data. So earlier the mesh density was very high. Now it got reduced. So we may think what is the advantage on it. So as I mentioned, the main advantage will be like the feasibility. So based on the system capability, so if I want to work freely, so then what I can do means I can do these kind of phase reductions and all. So this is what advantage of Decimate mesh body. So in that way, we can accelerate our reverse engineering, the process, the whole process. So once we done the decimation, directly I can go for the creation of solid bodies. Okay, actually based on our phase reductions, there are a lot of holes are happened. So that's why it is imported as a multiple solid bodies. So as I mentioned earlier, so whenever we are reducing the facets or whenever we are reducing the scan data, so we won't get an accuracy. That is a major problem. But actually this scan data is a very complicated curved surface. So that's why we are getting some these kind of error. But we have some simple geometry and we have a scan data with large number of mesh. So that is not feasible in our system. While working, it takes a lot of time. So if I want to reduce the scan data means directly we can go with the decimations. So now most of the regions are converted into solid. So we can see the solid data. So in this way, we can use SolidWorks for accelerating our reverse engineering process from the scan data or to a solid model. So I hope this gives an idea about the first scenario. So how we can work with the scan data in SolidWorks. So I hope it gives an idea. So we will move on to second scenario. So as we discussed in the initial stage, the second scenario will be like, we don't have any real object. We have only some image, reference image. So we want to develop a component, a CAD model based on an image. So in that occasion, how we can use the software. So we can see that second scenario. I will start with the new part. So obviously we all know, if I want to create some solid model, obviously I need some sketches. So we can trace an image and we can develop a sketch. So that can be done in all the softwares. So, but in SolidWorks, it will be a little bit quite easier. Say, for example, if I'm going with the sketch, so in the background, if I want a picture, so that it will be easy for us, we can trace out the picture and we can develop a model. So if that is the scenario, so easily we can bring a picture, either JPEG image or any kind of picture format on the background of your sketch plane. So to do so, I can go with the insert sketch picture, tools. So we have an option for sketch picture. So using that directly, we can bring down our images. Maybe I can select an image. So automatically image will be comes in our screen. Now I need to scan all the outer edges. So I want to scan all the outer edges. So to do so, we can do two kind of tracing. One will be manual tracing. Manual tracing in the sense, we can keep the picture on the background and we can use some sketch options and we can trace out the outer shape. Say for example, here if I want to trace out the outer means, I can use some spline option or line option and I can draw over the image. So this is what manual tracing. So manual tracing will be like manually we have to draw all the boundaries. But in SolidWorks, we have an option for auto trace. So auto trace in the sense software itself automatically trace all the boundaries. So whenever we have a single colored image, so based on the color also we can trace our images, the boundaries. I will show you. I can double click on my image. So once I insert the picture, so there is an option for next. I can go with the next. And here there are some selection tools are there for tracing. Say for example, I want to trace based on this color. So here there is a color picker is there. So I can use this color picker and I can select a color. I can simply select a color and I can go for begin trace. So if you see now, so automatically I got a sketch. I got a sketch on the boundary, a rough sketch. So here within a single click, we can able to generate the outer profile. So obviously we won't get 100% perfect tracing, but somewhat it can match the geometry. Actually, this tracing and all greatly based on the image resolution. So based on the image resolution, it is going to be traced out. But here our the image quality, the resolution is a little bit low. So that's why the tracing is not effective. And we can control the tracing. We can control in based on image brightness, where and all we want to scan, and the contrast, even the tolerance, the sharpness of the image, everything we can take in an account. Even the recognition, where and all it need to recognize. So with the help of this color picker, so quickly we can convert an image. Simply we can take a photograph and we can upload it to our system, and we can bring that image to the background, and quickly we can use auto trace things. Maybe I can hide the picture. So now we can see the sketch. So this is all about the second scenario. So from the picture, quickly we can generate a shape. Then we can go for a 3D design creations. Because generally, the 2D sketch developing is a time-taking process. So that can be easily addressed through these kind of sketch picture option. But as I mentioned earlier, so it is not going to be 100% perfect tracing, but we can use it. We can get some outer boundary. If you see here, I have got an outer boundaries. Only thing is near to the wheels and all, we are not able to capture properly. So this is what the advantage of sketch picture. Okay, fine. Now I have shown you based on the color, we have traced it out. In some occasion, we will have only blueprint, like a 2D diagrams. So we all aware, earlier for most of the component or anything, they used to keep some blueprints kind of thing, a reference image, 2D images. So even if we have those kind of image, so from that also easily we can develop a sketch. Maybe I can show another example. So this time I can go with some blueprint kind of thing or some orthographic views. So I have considered only a single image, just going with that. Okay. So here there is no single color. So based on color, it is complicated to choose our choose our boundaries for tracing. Obviously, for this also you can use a color picker because all the boundaries are highlighted as a dark black color. Maybe I can go with the next. Either I can use a color picker to select that black color boundaries. But only thing is there are a lot of intermediate lines and all. So it is complicated to trace based on the color. Okay, based on color, it's not happening. But what we can do means we can go with the manual selections also. Say for example, so this wheel rim seems to be unique. So I want to capture the designs, shape. Then I can go with the selection tools. So I can go with the selection areas. So rectangle area. So we can visualize the outer boundary. So based on the color picker, it traces out the outer boundary. So once I am okay with the outer boundary means I can go with the okay. maybe I can suppress. So I got the overall outer structure. So now this can be easily converted into a solid body or a surface body. So other modification can be easily done from the base model. So this is the one way. So as I mentioned about the other scenario, so if I want to select a particular area, if I want to trace out a particular area from an image, say for example, I want to trace out this rim shapes, then I can go with the next. Here I can use some selection tool. So I can select an area where I want to go with the tracing. So already a selection is there. So based on that selected region, automatically tracing will be happen. Actually, due to some graphics issue, it's not showing the selected region. Okay. So if we see here, so based on the selected region, automatically it got, wherever it is possible, the image got traced out and a sketch is developed. So as I mentioned earlier, it's not going to be more perfect, but maybe we can adjust the image brightness, so other parameters to somewhat match with the real time. So this is how we can use SolidWorks for the second scenario. That means, so we have an image. From the image, we need to develop a solid model. Again, this is also a part of reverse engineering. So hope this is also clear. So we will move on with a third scenario. So third scenario will be, we have a 2D data or 2D drawings. Either it may be done in any 2D softwares. So from the 2D data, we need to develop a solid model quickly. So generally for that, what generally most of the industry do means, they will see the diagram, they manually start sketching based on the dimensions, and they develop a 3D model. So we all might have seen a lot of engineering services companies. So they do these kind of 2D to 3D conversion. But for example, we have a 2D file. So say it's in a scale 1:1 scale, but they haven't mentioned any dimension. If that is a scenario, so it will take a lot of time to convert those 2D data into a 3D model. So first I need to measure all the parameters. From that I have to recreate a sketch. After creating sketch only, I can able to go for a 3D design. But in case of SolidWorks, easily we can convert a drawing file, 2D file into a solid model. So we will see an example for that, for the third scenario. So directly I can open a drawing file, like it can be done in any 2D software. So those drawing file can be directly opened in SolidWorks. Let me open a drawing file. So either I can import that drawing file into a 2D environment. Like in SolidWorks also having a 2D environment, drafting environment. So we can take all the DWG file directly into drawing environment. Or else say, for example, if I want to develop a solid model, obviously I need a sketch. So if I want to took this a DWG file, 2D file data into a sketch means directly I can go with import to a new pot. So I don't want it as a reference alone. I want it as a sketch. I can go with the next. Again, here I can control the units. Sometimes whenever we are working with the 2D data, so we don't know about the unit system. So roughly it can be 100, 200, like that. We generally go without units also. So in that scenario, if I want to scale down or scale up based on the unit system, so I can choose the unit system here. And even in most of the 2D files, they work with some layers. They control different boundaries or different kind of lines using a layers. So if I want to open up particular layers, so that can be also be done using selecting layers. So directly I can go with the next, finish. So now if we see here, so overall drawing can be imported in a single sketch. So obviously we all know these orthographic views. So each a sketch data will be relevant to a particular views. So if we see on this orthographic view data, there is no dimensions. So if we have a dimension means simply we can recreate the sketch and we can draw it. But here there is no dimension, but I need to develop a solid model. So based on the available input alone, then what I can do means, so once in 2D environment, we create all the views in a single page. So if I want to align each and every view on a particular plane, so that can be easily done here. Say for example, so this is my front view, this is my side view, and this is going to be top view. If I want to align each of this view to a respective plane, then what I can do means I can simply select, and on the left hand side, for this 2D to 3D conversion, there is a toolbar is there. So I can align this view to a particular plane. So I can select, so this is going to be my front plane. So I can choose a front plane, add to a front sketch. Now that particular portion unknown will be transferred to a new plane. And this one I want to align it in a top view, top plane. That means a perpendicular to this view. Then I can select these regions and I can align it to a top view or to a top sketch. So we can see the difference. Easily we can align. And similarly the other region, if I want to align in a side view, either right side or left side view, if I want to align, so I can go with the right sketch. So all these sketches will be aligned to a particular direction. Even sometimes we can align the sketch exactly matches with the other views also. Say for example, if I want to align this right view exactly from this point, that also can be done. Say for example, I can go with the exit sketch. So here there is a align sketch option also there. So sometimes it can be moved, but sometimes based on the reference, because it need to move a lot of entities. Sometimes it won't align, but we can check it out, okay? Okay, just give me a minute. I will reinsert it again. Maybe I can align it once again. We'll just check. Okay, no issues. As I already mentioned, so each sketch will have a lot of entities. So sometimes it is complicated to align because all the reference going to break. So to avoid it, maybe directly we can use the existing thing. We can simply align it to a respective plane. Then we can go with the solid model creation. Let me check one more time. Okay, no problem. Okay, even this is also more than enough for creating a solid model. So say for example, from the 2D diagram, 2D data, I just align each view on a respective planes. Now to convert this 2D into a solid model, so easily I can use the options. So if I want to extrude for the base, so obviously if I want to extrude or do any solid modeling operation, obviously I need some dimension. But as per this diagram, we don't have any dimensions and all. So in that scenario, so we can use these points, the sketch data as our reference. Say for example, this base should have a length of this much. So instead of measuring, I can give the starting point. So I want to start my extrude from a particular point. Maybe I can choose a point. From here, I want to extrude up to this point. So from the existing sketch itself, easily I can predict the reference. Similarly, that is for the cylinder also. Maybe once again I'm selecting, just I want to create the cylinder. I can choose this region. So here for the cylinder, from the top view, we can get some particular location from where to where I need to create it. So here also I can use a location points. So I want to start my extrude from this point. Sorry. So if we see here, we are not measuring any dimensions. So we don't have any dimension or anything. Just from a 2D drawings, whatever available information, we are easily able to create a solid models. Similarly, this cylinder, just I want to show you a quick small model. So for this also I can choose. We can use any views as our reference. Okay. Even this rib structure is also easily created. Maybe the top is not visible. I can enable it. So just with the help of these points, so we can get a final object. So this is how very easy when it comes to a converting 2D into a 3D. So we are not at all using any dimensions or anything. So based on the available 2D legacy data, we are just creating a solid model. So whatever operation we need, additional operation or modifying the geometry can be easily done. Say for example, if I want to add any features like fillets or chamfer or anything, so that can be easily done. So whatever operations or whatever modification from the existing object. So obviously we generally go with some optimizing the overall shapes and all. So that can be easily done once a 3D model is developed. So I hope this 3 scenario is clear. Gives an idea. So how we can utilize the software for our reverse engineering purpose. Either scan data or an image or a 2D drawings. So all these 3 things can be easily addressed using the tools. And apart from that, so obviously once we create a solid model, we generally go for some 3D printing and all. So for 3D printing also we can easily done some pre-works in SolidWorks itself. So the major thing about 3D printer is, so we have to get an idea whether our model is going to fit within a particular 3D printers or not. That's a major thing. So once we understand that, then only we can able to scale down. So how much I need to scale down? So based on the bed size. Say for example, if we have a 3D printer, means we know about the bed size of the 3D printer, particular 3D printer or print volume. But in case, for example, we want to outsource for a 3D printing. So we need to search for a particular vendor who is exactly going to match with the specification. Then if it is the case, we want to check in the SolidWorks environment itself. Say for this machine, sorry, for this component, whether it can done in a particular machines or not. Then what we can do is using SolidWorks itself directly, we can go with the file print 3D. So in that, so SolidWorks has included most of the printer machine data. So most of the 3D printer data are inbuilt with the SolidWorks. So the main purpose of the data will be, you can visualize the print volume in design environment itself. Probably we can't remember all the machine data and all. So whatever machines we generally work, we know the print volume. But obviously sometimes our model will exceed that print volume. So we need to outsource. So if we want to check here itself, then we can't go with the printers. I can go for a manage favorites. So here we can see a lot of printers. So most of the 3D printer data will be available with the SolidWorks. So easily we can choose a 3D printer. So whatever 3D printer we need. And on the right hand side itself, it show all the height, length and width of the print bed size. So whatever printer we need, we can choose it here itself. So I can choose the printer here, and here we can choose which face is going to match on the bed. So I can choose the face. So this is going to be the bottom side. So now I can visualize the print volume. So we can preview the shape. But the thing is, our model is not aligned properly. So it is somewhere beyond the origin. So we can easily relocate. So we can transfer the model, translate the model to a particular distance. So now we can see whether our model can be printed using that particular machine or not. So not only a single machine, it contains some extensive library. So we can choose some different machines. So we can select and check. So if you see here, so in this machine, we can't print our model. So all those things can be easily checked in the design environment itself. So if I see here, in only one direction, it is going out of the print size or bed size. So if I want to scale it down, so we got an idea. So I'm going to print my model using this printer only. These are my available facility. So when we check with that facility, so the bed size is not matching with our model. We need to scale down our model so that our model can be effectively print using that particular printer. So in that scenario, so we need to think, so up to what value I need to scale it down. So what value will be apt? So instead of thinking and instead of scaling like that, so directly here in software itself, we can go with the option called scale to fit. So once I give that option, automatically software will matches the diagram to fit within that volume. So I think it is considering all the sketches. Maybe I can hide the sketches and all. And another main problem is our model is away from the origin. So now I can check it. Yeah. So once I go with the scale to fit, so automatically it fits. So it chooses the effective scale value, 0.833. But manually we need to think to shrink what level we need to scale down or what value we need to scale up. So instead of checking like that, so directly we can do all those things in here itself. Even we can check the best orientation also. So based on effective printing, so I can choose orient to fit. So it can choose the effective alignment and all. So all this pre-work can be done. That is pre-work for additive manufacturing. That can be easily done in the design environment itself. Even if our system is directly connected to a printing machine, 3D printers. So directly we can print from the SolidWorks itself. So apart from that, we can choose the fill percentage and everything, or even we can preview the slice data and all. So I can go with the preview. So obviously it also shows. So where and all we need the supports. So maybe I can go with show faces that require supports. So in most of the occasion, we don't need any support, but only on these regions. So these regions, we need some support. So that and all we can easily check here. And even we can check the layer heights and all. So here a layer height is there. So it can generate a slice data also. So we can see the slice data. The edge length, everything can be controlled. And even based on the machine, it chooses the material also, ABS material. And finally, I can go with the OK. So if my system is connected with the printer, I mean directly it goes for a 3D printing. Or else, say for example, if our systems are not connected with the 3D printer, but we need to give a file to a printing vendor. So generally we all aware. So for 3D printing, STL will be a preferred. STL will be a preferred file format.
Excuse me, sir.
Yeah. Yes.
Yes. Whatever the what is the brown portion it is showing below the reference arrow?
Okay. Here, this one.
The brown portion. Yeah. The bottom
Outside
of
the boarding box, or
yeah. It is a square section where reference is there at the corner.
so
Or
this
that
one.
is the plane.
Yeah, this is just a reference plane.
You have clicking on that. This one.
Yeah, this is the reference plane. Only that gray area refers to our print bed.
Okay, can you orient this to the bottom?
Sorry,
No. In that direction. From the bottom of the printer, I can say.
Yeah, actually, sir. Actually, this is going to be the bottom of the printer. So which one I want to orient? Sir?
See, the component is rested on the top. Bottom face you need to orient. Yeah, I want to see the bottom face. Resting on the face.
Sir, actually, this face is going to rest on the print.
Yeah, that is fine. But along with the printer, I want to see.
Okay. Actually, here it shows only the volume. So this is where I have already aligned. So this is the base. So we can't see the whole printer, only the print volume.
No, that is fine. But I want to see the base, how the component is it rested correctly or not? Yes, it is rested on only two faces.
Yes, sir. These two phases.
Yeah. Okay, fine.
So actually, it
because
is planar.
In other software, what it can show all the particular contact point which are rested on the bottom surface.
Yeah, yes.
But here I can see only the corners.
No, sir. These two phases are only planar area. So these are all not going to rest, but based on the support. So generally for support, we can set some angle and all. Only up to this angle deviation. Beyond this limit only we need a support. So actually in real time, this curvature, the whole curvature, we can go with some support and all. But based on
that is fine. I am not question on that curvature. I am question on the red portion you are showing. Nearby that it is on the same plane. No, that red red. So it should show same color. No, it is rested on the surface proper.
Actually, sir, this red color shows our model.
Did you get what I?
Okay, sir. So it should be if it's shown in different color. So these phases are contacted or touch on the bed, like that you are asking.
Yeah.
Am I correct, sir?
Yeah.
Okay, sir. Actually, here there is no color difference, but since we are manually choosing the bottom planes, so here I can choose the bottom
fine.
plane.
In whatever I am practicing with some software now, they are not from SolidWorks, but they are specialized software, integrated software for
Yes, sir.
inter
Yes,
and this thing. So there I can see that okay, the face is rested correctly, and then we can go for print. Otherwise, we need to orient the model till the face is get rested properly.
Yes, sir. Obviously,
Yeah.
whatever you are saying is very correct, sir. Whenever we are going with some non-planar model, that will be very helpful. Whenever we see the faces are matches with the bottom plate or not. But here, since manually we are selecting it's not differentiating the contacted face.
The session is good. Okay, whatever you are saying is good and it is understood. See, because everything you are getting in only one software, na? That is
Yes, sir. Yes,
that is
yes,
fine. That is the beauty of this software actually.
yes, sir. Yes, sir.
Yeah.
So
Thank you.
obviously there are a lot of open source tools are there for to work with some scan data
Yeah.
as well as for 3D printing also, like Cura and
Right.
Blender. A lot of tools are there. So just to show how easily, because everyone we practice to go with some 3D designs and all. So that's
Right.
why I focus on this.
Right. And sir, one more question. So, can we measure the particular dimension from one face to other face if the model is selected for randomly and scan data is available for that? Can we measure?
Yeah, measure, we can measure, sir. But
Yeah.
to measure, obviously first I need to convert into a solid body.
Okay.
Then only I can able to measure, sir. Maybe I can just open a thing. So in general, we can't able to measure, sir. So once if I convert my graphics into a solid body, so once solid body is created, we can use some evaluate tools. There are a
Right.
lot of measuring techniques are there. So we can measure based on some points, location, and everything we can measure.
Hmm. Okay, okay. In this way, you are going to measure. But
Yes.
what is the accuracy actually? Did you check something with the actual models and this?
Sir, actually, the accuracy based on the scan data only, sir.
That.
Generally, we tried with some these kind of medical components, but that and all have a large number of mesh data, sir. Generally, they use some Artec 3D like that. They use those kind of scanners, so it's captured very effectively. So when we measure with that, its accuracy is like less than 1 mm only it is deviating. That is
Right, right,
based
right.
on the point data. But
Very.
in some occasion, these things are very large data.
Uh-huh.
Even in SolidWorks, it support the points also. Even without mesh data, we can open the cloud points alone. From the cloud points also, we can work on it.
Right, right, right.
Just to show you. So these are the just .xyz file format. Generally, whenever we are scanning with the cloud points, or even with the CMM, also now some digital CMM they measure, and it saves the report in .xyz format. So that also can be easily open in SolidWorks.
That is fine. Okay,
So this
nice.
is the point data alone. There is no mesh data and all. So these things also we can work it out on later stage. So that's the advantage. Even in
Good.
some occasions that CT scans and all, they go with some scan. So
Okay.
that can be converted into .xyz. Again, from the XYZ, that can be imported into SolidWorks. So
Okay.
that's the other way.
Okay, very good. Thank you, sir. Thank you.
Yeah. Welcome. Okay, just complete few more things like from the 3D printing. As I am explaining about the orientations and all, the main thing about 3D printers is now we generally prefer colors and all, colors, material and everything. But whenever we are exporting our file into a STL format, it captures only the model data, like the geometry alone. But say, for example, I want to share my model with the colors and everything to the vendor, 3D printer vendor, then that can be also easily done here itself. So if I go to save to a file, So there are different formats are there, STL 3D dot 3mf file and dot AMF file. So these dot 3mf dot AMF are some recent file format. So where we can go with some colors and everything for saving our file. They can go with the option just to show you an overview. So if we see here, so whenever we are exporting our file to a particular file format, that is required for additive manufacturing. So we can include materials as well as colors. So that is another advantage what we are using here. So usually we generally prefer to go with the STL file to give it some open source softwares or anything. But say for example, when we are giving our file to a vendor, those who are doing some 3D printing activities, so if we want to give with the colors, whatever we have applied for our model, if I want to include means we can include material as well as colors. Then it will be very easy for printing and all. We no need to explain like I need this color. Even some 3D printer, it goes with multi-colors also. So based on that, if I want to give all those information means I can go with .amf format, additive manufacturing file format, which includes material as well as colors. So this is also can be easily done for additive manufacturing activities. So hope with this I can end my session. Is there any queries?
Any questions?
This version is the official version. It is the license version. For students, is there any facility given by the SolidWorks to download it freely and they can work on?
Sir, if the host institution has the license, then
Okay.
there is an option for students to access student edition freely.
Okay.
But otherwise, they have to pay some nominal fee.
Right.
Like them.
And what are the other alternatives available for these softwares?
In terms of
suppose this is SolidWorks, is there any possibility in CATIA or other maybe Autodesk or maybe other 3D software?
For students, you are asking, sir, or generally you are asking?
This whatever you have tell me or whatever you have conducted this session on the SolidWorks is there any possibility it is available in other software too? Means 3D printing module and.
Yeah, yes, sir. It's available in some other software, other softwares also, but it lacks few options will be available, few options won't be available. Say for example, so this image processing and all can be easily done in CATIA also. So we can bring that and we can work on a scan data in CATIA also. But the thing is, only thing is the difference is going to be user interface. The accessibility and everything is going to change. It is available in other tools also, sir. So even I checked with the CATIA, so it's available there for image processing. But the thing is, the accessibility and user interface is drastically changed. So here, as I shown, simply I can right click and I can give that option. So that's the only thing advantage.
That means you should suggest this software for the learning and teaching also. This is good as compared to other software.
Yes, sir.
Yeah. Thank you, sir. Thank you.
Yeah. Thanks for your feedback, sir.
Hello, sir. So, what is the cost of this software, sir?
So it's based on the packages there, sir. Based on it, it will change.
Okay. Have you give any the company's colleges, sir?
Sir, we are supporting a lot of academic institutions, sir.
Okay.
So IIT, Palakkad, Kumaraguru, PSG. So we have supplied software, sir. So the autonomous institution also, MEFCO, NEC, Sastra University.
Okay. It is very useful, sir. Because the students have to learn a lot of things from this. They only know the basic idea of the SolidWorks. But if they are having this software, they are learning how to do the 3D printing and how to model this, how to create this. It's very useful for the students. Sir.
Sure, sir. Surely we will guide you on that, sir.
Okay, sir. Okay, thank you, sir. Any questions? Thank you, sir. So thank you for your session, sir. It was so nice. Thank you
sir.
for
Thank
your,
you.
thank you so much for sharing your knowledge, sir. Thank you
Sure,
for
sir.
your enlightening speech and enthusiastic participation. Once again, I thank you so much, sir. Thank you, sir. Thank you.
Thank you, sir.
Thank you.
Thank you all.
Thank you. So next, you can see tomorrow morning at 10 o'clock. Say we are having that test tomorrow. I posted that MCQ questions in the our Google form in your WhatsApp group, and having the time limit of 1 hour time limit 2 to 3. So after completing this your questions, you come at 3:15. You can start the validation function, and you can close that our APP. Okay. Thank you. Thank you.
Okay. Would you share some study material or?
Today I will share that, sir. PPT
Okay.
and
Sir.
all the
Okay.
materials I'll share, sir.
Yeah. Thank you, sir. Thank you.
Thank you, sir. Thank you, sir.
Bye.